Well, thank you, Jürgen, and I want to apologize for preventing you having the well-deserved siesta. Um, what I would like to do is to briefly present you the dramatic effects that deprivation of experience has on brain development. So, can I have the slides, please? Yeah. Um, yeah. Why brains of children and adolescents are particularly vulnerable. And I want to stress adolescence because development extends until the age 25. And there's very, very vulnerable periods also in late adolescence that should not be neglected. Supposed to move? Yeah. So, what is the neurobiologist's view on the brain? We are convinced that all knowledge resides in the functional architecture of the brain, which is the blueprint of the connections, is who talks to whom and how strong are these connections. That's all we have in the brain. It determines the programs according to which the brain works. And so it determines how we perceive, reason, decide, feel, judge, and act. There's nothing but this functional architecture. Therefore, all cognitive and executive functions are the consequence and never the cause of a neuronal processes. So we are emergentists, we are monists. We don't believe in mental causation. And also we are convinced that the neuronal processes obey the known laws of nature. So that has a lot of implications concerning free will and ethics. I won't discuss this topic today. So what are the determinants of this all-determining functional architecture of the brain? Of course, there are the genes, because they transmit the knowledge about the world that evolution has acquired by natural selection. Only those brains have survived that work according to programs that are adapted to the challenges of the world, the small aspect of the world in which life has developed. And the genes, they determine the basic layout of the connectivity. But there is also very much epigenetic shaping occurring during development because the genes can't anticipate everything. There are a lot of refinements necessary that can only be accomplished if experience with the real world is available. Because this experience adapts the architecture to the actual conditions of the environment in which the organism evolves. And the mechanism consists in the fine-tuning of connections, and I will give you examples. And then there's, of course, lifelong learning, which continues from childhood to senescence. And after the development of the brain is finished, which is about the age of 25, when no new connections are formed, and normally no connections disappear, then there is still the ability to fine-tune the efficiency of the connections by what we call synaptic plasticity. So I will give you some examples of genetically determined architectures that are not so much under the influence of epigenetic effects. And this is, first of all, the topological arrangement of processing modules. If you take the cerebral cortex, we can distinguish about 120 different areas that have different functions. Intrinsically, they all operate according to exactly the same algorithm, but their functional specialization depends on their input-output connections. So the visual system gets input from the eyes, the auditory system inputs from the ears. They process the incoming signals according to the same principles, but because they get input from the eyes, we call it the visual system. Also very well determined is the connectivity among the modules, among those different processing nodes. And here's a nice picture that one can nowadays get with magnetic resonance tomography. It shows the long-range pathways in the human brain of a living human being with amazing resolution, and one can follow the path of these connections from one area to the next. What one can do more invasively in animal experiments, in this case, the subject is a macaque monkey. one can trace these connections from one area to the other with fluorescent dyes, for example. And then one gets this amazing complexity of the network. But you see here the red dots in the graph, they correspond to each one of those colored areas that I have shown you on the hemisphere before. And the white lines in between, they are massive reciprocal anatomical connections that where neurons talk over long distances, mainly in a reciprocal way. And these long-range connections, they also lay it out genetically. They are comparable in every brain, but they can still be fine-tuned with regard to their efficiency. Now there is the general layout of connectivity within modules. Also in the microstructure of each area, there is a very sophisticated connectivity. For example, in the cerebral cortex, we have 6 layers depicted here. We have functional columns that are devoted to particular extraction of features. And the neurons therein, and in about 1 cubic millimeter, there are about 60,000 of them. And the cables there are about 6 kilometers, which interconnect those neurons. And the blue lines that you see here, they are also canonical. They are genetically fixed. They are found in the same way in every cortical area. Also across species, there's great similarity between monkeys and man, for example, but even mouse is a good model. And then there are these red lines, which I will be talking about in a moment, because they are the ones that are very much susceptible to epigenetic modification, to experience-dependent modifications. Now, what is very important to retain is that development of the brain occurs in phases, and we call them critical periods. There are windows of opportunity that open for a particular brain area. During that time window, experience needs to be available in order to allow the brain to mature properly. And then these windows close again, and thereafter, the changes that have occurred are irreversible, because there is no longer growth of connections, and there's no longer the option to remove connections. One should retain that in the developing brain until puberty, about 30 to 50% of the connections that are newly formed during development get disrupted again. They disappear due to experience-dependent pruning, as we call it. And as I said already, this process lasts until age 25. Thereafter, the architecture crystallizes, and all the learning that is still possible has to occur by changing the efficiency of the connections. Now, there's an interesting temporal progression of these critical periods from lower brain centers to higher processing modules. The basic sensory functions like being able to use the eyes for vision, ears for decoding sounds, they have critical periods which in the human baby last, or a child last about up to age 5 or so. Then more complex sensory motor functions, coordinations, mastering a musical instrument, the critical period sets in later and is finished by the end of puberty. And then there's another very important and often neglected critical period. This is during puberty and early and late adolescence, where social competences are acquired. And also these processes, they follow exactly the same mechanisms of outgrowth, of formation of connections, testing the connections functionally. If they are not usable, destroy them again. And also these changes are irreversible. So very important changes that occur during critical periods under the influence of experience, they are irreversible. So very early on in development, even the long-range connections that are genetically determined, and you find them in every being of the same species, they can be removed if they are not functionally consolidated. The best examples, they come from Hubel and Wiesel, who got the Nobel Prize for this discovery. Normally, you use your two eyes simultaneously for stereopsis, which means you have to have neurons in the visual cortex which receive inputs from both eyes. In order to make this function precise and possible, you need to connect those cells in the two retinae selectively with particular target cells in the cortex. This cannot done by the genes because it depends very much on how big the skull will be, where the eyes will be located, and so forth. So the nature relies on experience in order to do this fine-tuning. The consequence of this is that if one deprives a young child of vision in one eye, which in former times occurred quite often because of postnatal infections, the fibers from this eye to the target cells in the brain get completely disrupted and they never grow again. It's an irreversible loss of one eye. You have something related in strabismic children who cannot get the images in the two eyes in register, and they end up with two populations of neurons in the brain, one driven by the right eye, one driven by the left eye. This is irreversible. They lose depth perception, stereopsis, as we say. There is a very important rule that dominates all these critical period-dependent fine-tunings. This is neurons that fire together, that are very often activated in synchrony, they wire together. And if this is not the case, they will lose their connections. And this is used for fine-tuning of connections and for acquisition of the statistical regularities of the outer world in order to imprint this into the connectivity so that the brain is able to acquire a model of the world, of the statistical regularities of the world in which the subject evolves. And this fine-tuning leads to anatomically visible changes in the connectivity. And now I'm talking about these red connections that you see here. These make up about 80% of the connections between neurons in our cerebral cortex. They are reciprocally connected through these red connections that I depicted here. And they can be traced very easily. One can inject small doses of fluorescent dye, as you see here, green and red, into particular functional domains that are depicted in black here. If one does this in an adult animal, in this case it's cat, but it could also be in monkey, and this very same process must occur, even though we don't have this direct evidence in human brains, but processes are very similar. One can label those connections, and then one finds in the normal adult who went through a critical period with unrestrained experience that you see here the red and the yellow dots being precisely superimposed on these functional domains that are labeled in black. A very high degree of specificity, which, however, emerges only and only if the animal or the human child had the chance to have access to visual experience, because only then do these neurons display the correlated activity that is required to fine-tune those connections. If one raises an animal in the dark, the connections remain random. You see these green dots, they are all over the place, there's no specificity. If one raises an animal in the dark beyond the critical period, it stays blind for the rest of the life. And you must imagine that the same processes occur also for the higher cognitive functions. It's not only for these very primitive early developmental stages. Now I want to emphasize that there is another very vulnerable phase in adolescence. There is a transition, and Freud called this the second chance. Apparently he knew about there being a critical period during which you acquire certain competences which you have to acquire during that period, otherwise you will have no chance to recover from that. And what one sees, and now I'm talking about electrical activity, a very characteristic signature of brain activity is that neurons tend to oscillate. They have periodic response patterns. And this is used in order to coordinate the processes in different brain regions by synchronizing this activity. So one can measure the synchrony, also human beings, by recording EEG or magnetoencephalographically, and then one gets a correlation measure. And if one does this from development, and this is a longitudinal study starting at 6 years old until adulthood. And now it's a bit crowded, I apologize. If you look at the 3 curves that have red arrows, in the adult, you see a nice peak, which indicates that there is a network that is very well synchronized. And this is on the graph, the black bar, the black lines in this skull picture on the lower part. I don't have a laser picture pointer, unfortunately. So high degree of synchrony, very compartmentalized hubs of processing areas. You see something similar in late childhood. If you take one of these upper skull graphs, there's a lot of synchrony, but it is globally distributed. The networks are global, they are not focal. And then in late adolescence, you see the red arrow on bottom, there's virtually nothing of this wonderful coordination. The proton network that is established in children and is global breaks down completely to give way to another network that is much more focal, has hubs, and gets much more under the control of the prefrontal cortex. This is where the higher cognitive functions are accomplished. And this is a very vulnerable phase, and it just so happens that this developmental phase coincides precisely with the first manifestation of schizophrenia. So if early diagnosis is attempted, one sees that it starts at around this time, and the electrographic signs are of that kind. These patients are not able to establish the nice focal synchrony patterns that you find in the adult. Now, another very important point also for this discussion here is that these developmental processes are not sustained by passive exposure only. What is required is that the organism actively interacts with the environment, asks questions, and selects the information that it requires for its development. There's a nice classical experiment by Held and Hind, who raised kittens in the dark, so they had no access to visual experience. Then they put them in a carousel, each one in a gondola, and one was able to move the carousel because it was allowed to walk on the ground, and the other was just sitting in the gondola. Both saw exactly the same environment over time, but the kitten that was passively moved by the other one never learned to see, never learned to use their eyes. This illustrates how crucial it is to have active interaction with the environment and select the signals that you need in order to mature your brain properly. And we know the centers in the brain that are responsible to gate this plasticity, to gate these early learning processes, and they are closely related to motivational systems. And that's why it's so important to know that passive exposure alone is simply insufficient. You won't make it. Now, just to give you an intuitive example of how important it is for our being in the world and having a model of the world, that this knowledge is acquired through early experience. Because this knowledge that is acquired through this fine-tuning, experience-dependent fine-tuning in our environment, being it real environment or cultural environment, doesn't really matter. It determines how we perceive the world. And therefore, and since we have to take for granted what we perceive. People being raised in different environments, having different priors, having different fine-tuning of the architecture, will perceive the world in different ways. But there's no way to convince them that their way to perceive the world is different from ours. You have to take it for granted. And here's the example. I tell you that the square A and the square B have exactly the same brightness. You see B, of course, much brighter than A. But if I take the context away a little bit, you will see that A and B is exactly the same brightness. Why is that? The brain as a whole sees that there is this green column that throws a shadow over B. Now, since is the same number of photons coming from B and from A, as you just saw, because they have the same brightness, the brain calculates, well, if there's a shadow and I still see the same amount of photons, it must be brighter. So the brain calculates brightness without you being aware of doing this. And this is the case with all sorts of perceptions. The brain offers you an interpretation that it arrives at given the priors that are stored in its functional architecture. So the conclusion is the functional architecture of the brain represents the internal model of the world. It determines how we perceive, reason, feel, and act. You just saw an example. And this architecture is shaped essentially by interaction with the environment. And after the end of the critical periods, these changes become irreversible. So what are the consequences for this conference here is, if the development of functional architectures is increasingly guided by exposure to virtual environments, what does that mean for our model of the world? If exposure is passive, precluding active manipulation of the environment, which is video watching, screen watching, what does that mean for our ability to build a realistic model of the world or to fine-tune our connections? And then finally, if social interactions are replaced by remote communication, what does that mean for our critical periods? And let's discuss whether these factors could be equivalent to deprivation. And that's the question that I want to throw in the plenary and leave you there. Thank you.